Okay, and this will be the third and the final video of 3.7. This is on writing rational functions and then on oblique asymptotes. So here we have like kind of a very mathy definition here. The idea here is that if I know the intercepts, the horizontal intercepts, and the vertical asymptotes of a function, of a rational function, then I can write the function using that knowledge, and by determining from the graph what the powers on those asymptotes and what on those roots are. So, or on the factors that give us those. So, let's look at an example. Oh, and of course, I have to keep in mind that there could be a stretch factor here in front. So I always want to write this a in front as well whenever I'm looking at this kind of thing. So let's look at an example. Write an equation for the rational function graphed here. So first we want to take note of any kind of information that this gives us. This gives us that I have horizontal intercepts at x equals -2 and x equals 3, vertical intercept at y equals -2. Notice how this function seems to be leveling out at towards the line y equals 0 at its endpoints. So I'm going to say that this has a horizontal asymptote at y equals 0. And this has vertical asymptotes represented by these red dotted lines also. Sometimes these are represented by dotted lines. This has vertical asymptotes at x equals -1 and +2. Notice at this x equals -1 asymptote, the branches are going in opposite directions. This implies that there's an odd power on that asymptote, or on the factor that gives us that asymptote in the denominator. And at x equals 2, the branches of this graph are going in the same direction. This means that there's probably an even power, or not probably, but that there is an even power on the factor that gives us this particular asymptote. Let me see. At these horizontal intercepts, I don't think anything weird is happening, right? It looks like they're passing through the graph relatively linearly. So it seems like the multiplicities on these will both be 1. Let's use the information we have here and put this, try to piece this function together. So I have horizontal intercepts at x equals -2 and at x equals +3. So this gives me the factors x plus 2 times x minus 3. In my denominator, I have, let's see, I have x plus 1, which gives me this asymptote at x equals -1. I have x minus 2, which gives me the asymptote at x equals 2. And the x minus 2 one will be squared because the graph is heading in the same direction there. So this has to have an even power on it. And I have some kind of stretch factor in front of this. I have some kind of stretch factor A. In order to determine what that stretch factor is, I have to use this vertical intercept that I was given here. I have a vertical intercept at y equals 2. This means that I have the point, or at y equals -2 it was. This means I have the point 0, -2 on my graph, or that f of 0 is equal to -2. So what I want to do is I want to find f of 0 and solve for a, because I know what f of 0 should be. F of 0 is 0 plus 2 times 0 minus 3 all over 0 plus 1 times 0 minus 2 squared. F of 0 was negative 2. So this is a times 2 times negative 3 is negative 6 over 1 times 4 is 4. So I get negative 2 is, let's see, this simplifies to negative 3 halves times a. I multiply both sides by negative 2 thirds to undo this multiplication by negative 3 halves on the right hand side. And this gives me 4 thirds is equal to a. So I take this function and I replace a with 4 thirds, which gets me f of x is equal to 4 times x plus 2 times x minus 3 over 3 times x plus 1 times x minus 2 squared. Let's look at a new concept altogether. So previously we saw examples of rational functions that didn't have horizontal asymptotes, because not everything has a horizontal asymptote. But we do have something that lets us describe the behavior of the long-run behavior of a rational function that doesn't have horizontal asymptotes. This is an idea called oblique asymptotes. We'll get a definition in a second. If I want to describe the long-run behavior of 3x squared plus 2 divided by x minus 5, notice there is no horizontal asymptote here. However, I can perform some polynomial division so I can get a better understanding of how this graph behaves. So let's perform polynomial division. I have x minus 5 on the outside. On the inside, I have 3x squared plus 0x, I need that placeholder, plus 2. X goes into 3x squared, 3x times x minus 5 is 3x squared minus 15x. I subtract. This is 15x plus 2. I bring down that 2. X goes into 15x 15 times, so plus 15. 15 times x minus 5 is 15x minus 75. I place parentheses around this, and I subtract, and I get a remainder of 77. So this means that 3x squared plus 2 over x minus 5 can be rewritten as 3x plus 15 plus 77 over x minus 5. Notice that as x becomes really large in the positive or negative direction, 77 over x minus 5, well, I would be dividing this by a larger and larger number. So this term is going to go to 0 in the long run. This means that for this particular function, as x approaches plus or minus infinity, f of x approaches the line 3x plus 15, which is the quotient I got from this division just without the remainder portion. So I call y equals 3x plus 15 the oblique asymptote of this function. This is the oblique asymptote of this particular function. So to explore the long-run behavior of a rational function, we can perform polynomial division, and then the quotient will describe the asymptotic behavior of the function. When this result is a line, we call this an oblique asymptote or a slant asymptote. Let's look at another example. Let's go ahead and use synthetic division for this one. Well, if x plus 1 is equal to 0, x is negative 1. Negative 1 goes in this box. Then the the coefficients of this polynomial, of this quadratic, are negative 1, 2, and then I have 1. Negative 1 comes straight down, times negative 1 is 1, plus 2 is 3, times negative 1 is negative 3, plus 1 is negative 2. I have a remainder of negative 2. This means that x squared plus 2x plus 1 divided by x plus 1 is equal to, this is negative x plus 3 plus negative 2 over x plus 1. Notice that this term is going to become insignificant as I go out towards positive or negative infinity. So my oblique asymptote here is just y equals negative x plus 3. And also, while we typically only concern ourselves with oblique asymptotes, we can describe other kind of asymptotic behavior using the same concept. Let's describe the long-run shape of this function. Once again, let's perform synthetic division. If x plus 1 is 0, then x is equal to negative 1. So negative 1 goes in the box here. Then I write the coefficients here, negative 1, 4, and 2. I'm not missing anything, so this negative 1 comes straight down. Negative 1 times negative 1 is 1, plus negative 1 is 0, times negative 1 is 0, plus 4 is 4, times negative 1 is negative 4, plus 2 is negative 2. So I get a remainder of negative 2 here. This means that negative x cubed minus x squared plus 4x plus 2 divided by x plus 1 is equal to, let's see, this starts with the cube term, so this term is a quadratic. This is negative x squared plus 0x plus 4 plus negative 2 over x plus 1. Or let's see, did I do something wrong here? Oh, let me see. I don't think I did something wrong here. I think that the worked example here actually has something wrong with it. Yeah, okay, I'm correct. Okay. Now notice again that this last term here, this last term is going to be insignificant in terms of the shape of the graph as I go out towards positive or negative infinity. So in the long run, this function behaves the function behaves like f of x equals negative x squared plus 4, which is a downward opening parabola or a concave down parabola. And that's it for this last part of 3.7.